Hello! In the last video, we talked about dispersion forces and dipole-dipole forces. In this video, we're going to talk about two stronger forces, hydrogen bonding and ionic bonding. So hydrogen bonding isn't really a bond, it's still just an intermolecular interaction. So I'm going to put quotations around bonding here. Now, hydrogen bonding is going to occur between molecules that have a hydrogen atom bonded to either oxygen, nitrogen, or fluorine. The reason for that is oxygen, nitrogen, and fluorine are particularly electronegative. So instead of just a regular dipole-dipole interaction, between molecules that have these specific parameters, we're going to see a slightly stronger interaction called a hydrogen bond. So one example is water. Water molecules, of course, have hydrogen and oxygen, and notice that there are these forces that exist between the hydrogen of one water molecule and the oxygen of another water molecule. So this is hydrogen bonding. And the reason for this, we know oxygen is particularly electronegative compared to hydrogen. So oxygen has a partial negative charge, hydrogen has a partial positive charge. And that's going to be true for each water molecule. So the partially positive hydrogen is attracted to the partially negative oxygen on another molecule. So again, hydrogen bonding is just a particularly strong type of dipole-dipole attraction. Now this becomes really important in structures like DNA. So DNA, also called deoxyribonucleic acid, is found in every living organism and contains our genetic information. Now, DNA consists of two anti-parallel chains of repeating nucleotides. So we get a helical structure. So down below, you can see we've got these two strands, and they're kind of wrapping around each other and forming this helix. And in the middle, we have nucleotides that are attracted to each other through hydrogen bonding. So on the right-hand side, this is just showing a more detailed version of DNA, but in the middle you can see the hydrogen bonds that occur, and this is what's holding our DNA together. So notice we've got a hydrogen on a nitrogen atom, and that's attracted to the oxygen on the other side of the DNA molecule. And down below, again, we've got a hydrogen bonded to nitrogen, and that's attracted to the nitrogen on the other side. So going back, again, as long as you have a hydrogen that's bonded to oxygen, nitrogen, or fluorine, it will be attracted to other oxygens, nitrogens, and fluorines. Now, if you have trouble remembering this, I use the phrase hold the phone, F-O-N. And that helps me remember the very specific parameters for hydrogen bonding. Okay, so let's practice identifying whether a molecule exhibits dispersion forces, dipole-dipole forces, or hydrogen bonding. So remember, nonpolar molecules exhibit dispersion forces. Polar molecules exhibit dipole-dipole forces. And then if you have a hydrogen bonded to oxygen, nitrogen, or fluorine, that will exhibit hydrogen bonding. So pause the video, try to identify the type of intermolecular force for each of the molecules below, and then we'll go over it together. Okay, let's look at oxygen. So remember, oxygen has two oxygens and they have a double bond between them. And whenever we have two of the same atom bonded together, that's automatically going to be nonpolar because those atoms have the same electronegativity value, so they're going to equally share electrons. So this is a nonpolar molecule. So what type of force do we expect? Dispersion. So if we had another oxygen molecule nearby, these two oxygen molecules would only exhibit weak dispersion forces, and that's actually why oxygen is a gas, because it doesn't have very strong intermolecular interactions. All right, let's look at HF, hydrofluoric acid. So right away, I can see we have a hydrogen bonded to fluorine. So that tells me that this will exhibit hydrogen bonding, or H bonding. So I didn't even need to look up the electronegativity values. Just right away I knew this will exhibit H bonding between two HF molecules. So if we look at two HF molecules, the hydrogen on one of those molecules will be attracted to the fluorine on the other molecule. And that will be a particularly strong interaction compared to dipole-dipole interactions. All right, and then let's look at H2S. So this is going to look pretty similar to the structure for water. So we're going to see that bent or angular shape. And if we look up the electronegativity values, sulfur is 2.5, hydrogen is 2.1. So electrons are going to be more attracted to sulfur, and that's going to create a polar molecule. So which force would we expect? Dipole-dipole. So again, that electronegativity difference between sulfur and each hydrogen is 0.4. And so that would fall into our polar molecule category. Okay, so now that we know the forces for each of these molecules, let's list them in order of increasing boiling point. So again, oxygen exhibited dispersion forces. HF, hydrofluoric acid, exhibited hydrogen bonding. And H2S exhibited dipole-dipole interactions. So dispersion forces are the weakest, so those should be the easiest to break apart. So would we expect the boiling point to be really high or really low for oxygen? Really low, right? Because it doesn't take a lot of energy to separate those oxygen dispersion forces. So we'll put O2 as the lowest boiling point. And then the next strongest force is the dipole-dipole force for H2S. So since that's a little bit of a stronger force, it should take more energy to break apart those H2S molecules. So H2S will have the next highest boiling point. And then finally, hydrofluoric acid exhibits hydrogen bonding, which is much stronger than dipole-dipole interactions. And so it's going to take even more energy to try to break apart those HF molecules and get them boiling and turning into a gas. So that will have the highest boiling point. Okay, Now, the last type of intermolecular force is ionic bonding. So we talked a lot about ionic bonding in chapter 3, and we saw that ionic bonding occurs between two ions of opposing charge. So a positive ion and a negative ion. So ionic interactions can be considered another type of intermolecular interaction. Now, back in chapter 3, we also talked about how substances that contain ionic interactions are relatively strongly held together. So ionic compounds typically have really high melting points and really high boiling points. In particular, we looked at sodium chloride, and sodium chloride is just table salt. And if we could zoom in on one of the crystals from table salt, we would see a crystal lattice where we have alternating chloride ions and sodium ions. So we're not going to focus too much on ionic bonding because we've already talked about it in the past. But let's sort of summarize all of the forces we've seen, and we'll talk about how that relates to boiling points, or the energy needed to break apart molecules and turn them into a gas. All right, so in order for a substance to enter the gas phase, its particles must completely overcome the intermolecular forces holding them together. So, if we compare boiling points between molecules, that's essentially equivalent to comparing the strengths of the attractive intermolecular forces that are exhibited. So let's look at these first four substances in the table below. We have hydrogen gas, neon gas, oxygen gas, and chlorine. And notice that these all exhibit dispersion forces, and they're all typically found as gases at room temperature. We can also look at their boiling points, which are all really, really low. They're all negative. So these molecules are really easy to boil, and that's why they're always going to be gases at room temperature. Now let's look at the next three molecules. We have HCl, HBr, and H2S. And these all exhibit dipole-dipole interactions. Now their boiling points are also negative, but they're generally going to be higher than our gases. So these molecules are typically liquids at room temperature. Now the last three, NH3, HF, and H2O, they all exhibit hydrogen bonding because they have a hydrogen bonded to either nitrogen, oxygen, or fluorine. And their boiling points are a bit higher. So typically, these are going to be very polar liquids at room temperature. So these are a little more difficult to boil because they do have those stronger hydrogen bonding interactions. Now that brings us to our different states of matter, or different phases of matter. So again, we have solid, liquid, and gas. So on the very first slide of chapter 8, we talked about how intermolecular force strength increases as we go from gas to liquid to solid. So down below in our table, we can see that the relative intermolecular interaction strength is really strong for solids, moderate for liquids, and weak for gases. So most likely solids are going to exhibit ionic bonds. And of course, there's always exceptions to that, but for the most part, we'll see ionic bonding with our solids, or even covalent bonding. Moderate interactions will result in a liquid, so that could be dipole-dipole interactions or hydrogen bonding. And then for gases, we're typically going to see really weak dispersion forces between the molecules. All right, now this is also going to give us the reason why we have a definite shape and a definite volume for solids, because everything's held very tightly together. And then we have an indefinite shape and definite volume for liquids. So the liquid molecules are very attracted to each other, but they can still kind of move around. And then for gases, we have both an indefinite shape and indefinite volume, because they have such weak forces between the molecules that they're just going to roam around and do their own thing. They're not really held together. Now, one interesting case is water. So earlier we said that water molecules exhibit hydrogen bonding. Now, because of this, water molecules are going to maintain the liquid phase at higher temperatures than expected. And we can actually see a model of water molecules off to the right. What's interesting though is as we decrease the temperature and turn water into ice, we see that the solid form of water is less dense than its liquid form. So that actually allows ice to float on liquid water. So notice in the solid water picture, we're forming these almost hexagon shapes between the water molecules. So that's going to create less mass per volume for water. And remember, if you have the equation for density here is mass over volume. So if there's less mass per volume, the density is lower. In fact, the density of liquid water is about 1 gram per centimeter cubed. And for ice, it's about 0.9 grams per centimeter cubed. And that's why ice floats, because it has a lower density. And then water is also special because it's an excellent solvent, which means it can dissolve other substances, and that can allow those substances to react with each other. All right, so I think we'll stop the video there today. Next time, we're going to start talking about gases. And in particular, we're going to see that gases have very specific laws and relationships. So we'll talk about that next.